Thank you. I'd like to thank the organizers for inviting me to this symposium and workshop. Well, slight misnomer in the topic, because it should be advanced numerical method, because I'm just going to talk about one method here. There are several methods out there which are typically kind of quoted as the future methods for modern computer architectures. I'll be talking about mainly about one. So the brief outline of my talk would be, what is the need for newer numerical methods? Why are we, first of all, trying to not essentially recreate the wheel, but why are we trying to migrate to these newer kind of methods? Is there really a need for it? Because we have had things going on for many, many years, and things seem to be working out quite well. Specifically, I will talk about the discontinuous Galerican method, which I think is one of the solutions, one of the several solutions out there for the newer kind of computer architectures. And then I will talk about one application of the DG method to tsunami and storm surge modeling. Okay? So if you look at it, the growth in supercomputing power has been tremendous over the past couple of decades. So this is a plot which I took from Wikipedia last night, and you can see, so on the y-axis, you have gigaflops, okay, in a log scale. So gigaflop is 10 raised to 9 floating point operations per second, and you can see that over the years, so the red line is the fastest supercomputer in the world. So in 1993, we were just about below 100 gigaflops, and today we are in the regime of petaflops. The fastest supercomputer in the world today does something around 30 peta floating point operations per second. And the blue line is the sum total of the floating point capacity of all the top 500 supercomputers in the world at that given point of time. And you can notice back in 1993, this was about 1 teraflop. Today, your desktop computers can do 1 teraflop. So the computing power that you have in your hand today exceeds the sum total of the top 500 supercomputers back just about 20 years ago. So it's a phenomenal amount of compute power that we have today. But are we really utilizing it for efficient science? Are we able to do the sum total of science which the top 500 supercomputers did 20 years ago on our desktop today? Answer is obviously no. We're not able to extract the maximum capacity of science which this phenomenal growth offers us. So what is the roadmap? And now people are talking about extrapolating this and going towards exascale computing. Okay, so we're talking about building larger and larger machines. I was just, IIT Kanpur has just got a 300 teraflop machine. That's a significantly large machine. And we're talking about spending a significant amount of money in building petaflop machines even in our own country. Okay, so first of all, is there a need for exascale computing? That's a big question to answer. I sincerely believe there is a need for exascale computing because the kind of problems that we want to tackle, we want to add more and more complexity. We want to do larger and larger degrees of freedom. So I definitely believe there are applications out there which will utilize, if not exaflop computing, at least petaflop computing. And if you have several petaflop applications, then an exaflop machine is a must. Okay? The third question that comes is, what is the architecture of this exascale machine? Okay? If you look at the evolution of computer hardware, right? So when I was growing up, if I just wanted to get a faster machine, I just had to wait 6 months. Instead of a 60 megahertz machine, a 120 megahertz machine would come, and it would work twice as fast. And things would progress in a nice linear fashion. But in the last 10 years, we have seen a dramatic change in this. So we have started hitting physical limits of clock speeds, computer architectures have changed. I mean, we can spend an hour trying to talk over here why computer architecture has changed. Okay? So fundamentally, we are going into the era of multi-core or many-core computing back again. We are going back into the era of vectorized machines. So we started off in the 60s and 70s talking about vector computers. Okay? Then the microcomputer boom took over, We started doing everything on microcomputers, started building larger and larger microcomputers, faster and faster sticking together microcomputers, but then now we're going back to the era of vector computing when you talk about accelerators, so on and so forth, which I'll come to with them. The last and the most important question is, are the current numerical methods which we use adequate and scalable when it comes to exascale? So the common understanding is that if I have a machine which is 1,000 times faster, or if I have 1,000 processing cores, my code should run 1,000 times faster. But that's a very naive way of thinking. In reality, that's not what happens. You realize there are physical limits because there are communication bottlenecks. Okay? So every numerical method needs to communicate. The moment you partition your problem and spread it out to, say, n processing cores, there is a cost of communication between these n processing cores, and that starts biting you. So you want to minimize your ratio of communication to computation as far as possible. And whether our existing numerical methods have that property is the question which we need to answer, and whether we can improve that is what we are looking at. So there is something known as the Gordon-Bell Prize. Okay? So this prize is awarded every year at the supercomputing conference to the application which uses the largest amount of floating point calculations in a sustained manner. Okay? So basically which will become the largest compute for that year in some field of science. Okay? And you can see as we go down, as we go ahead in time, you started seeing an increasing amount of use of computing power. Okay, so there's some data missing about the efficiency. But actually, as you are going in 2012, you see that a 4 petaflop compute is actually only 42% efficient. Okay, so that means that for 58% of the time, the CPU is actually sitting idle. It's not doing any compute. And the reason being, it comes back down to the same communication to compute ratio. You're waiting an incredible amount of time to communicate the data which is required for computing, and the CPU just idles during that time. Okay? So the goal is we want to improve this efficiency. And once we improve this efficiency, only then can we claim that we really are scaling our applications to these millions of processing cores, if possible. Okay? Now, let's look at a typical finite volume stencil, right? I mean, this is what most CFD people like to look at, most mathematicians would look at. So I want to compute a gradient at this point. Now, if I want to compute a gradient at this point with second order accuracy, I need information from here, 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 and here. Same applies for finite difference as well. The moment I want to go for any higher order of accuracy, my communication stencil becomes larger and larger. Okay? I need information from all these surrounding data points. And if this point sits on a boundary where I have partitioned my problem, and say half the data is on another computer and the other half sits on another computer, it could be at an intersection of multiple processing cores as well, the amount of communication that you need to do to just compute a higher order gradient over here is going to be tremendous. And this is going to start hurting you very, very, very soon. Okay? We might mask issues like this by trying to do more degrees of freedom, in the sense that, okay, if I'm just looking at a simple advection type of problem where I just have to do U, V, and W calculation, but I can add more complexity to it. Like, I could start doing combustion, I could start doing few other species transport, I could add a lot of other vectors into it, and I could mask that communication problem by adding a little bit more compute. But if I want to do very, very simple calculations, like things like, say, for doing meteorological or weather prediction calculations, where the number of vectors is actually very few, you will start hitting this wall very, very quickly. Okay? And this is classically, okay, yeah, just before I go ahead, so this is a typical sparsity pattern of a finite volume stencil. Okay? If you look at the matrix of a finite volume stencil, you will see something like this, which is fairly sparse and fairly, the bandwidth of this matrix is quite wide. This is an unordered matrix. There are some reordering algorithms which you can make it more efficient. Okay, so this is ordered by using reverse Cuttle-Mekki, and you can still get a banded matrix, something of this sort, but it is still very, very sparse and very, very empty. So the communication pattern of this, this kind of method is not that great. And because of this kind of matrix structure, your parallel scaling becomes very weak. So this is parallel scaling of a very popular open source CFD code called as OpenFOAM. Okay, this is for a sample test problem of a lid-driven cavity. Okay, simple incompressible flow, and you're trying to scale this problem. Okay, and you're trying to scale it with different degrees of freedom in the the size of the problem. And this yellow line, I apologize, it's not quite clear, but if you see this yellow line, this linear yellow line, is the ideal speed up. Okay, so if you increase your processor count by n, your speed up should be n. Okay, you see that as you keep increasing the number of processors, obviously for the smallest problem you start flatlining very soon. You don't get speed up beyond about, this is roughly about 200 processors. Okay, if I increase my problem size to about 27 million grid points, I still see that at about 2000 processors, I cannot scale my algorithm anymore. Today's fastest supercomputers are having more than 1 billion processing cores. So theoretically, I cannot even use a fraction of that computing power if I stick to my classical finite volume kind of methods. Okay? So this is where I say, if I mask it with something like, okay, this is a simple incompressible flow calculation. If I add a combustion calculation to this, yes, this point will shift further away because my amount of compute is increasing. But then if I really want to scale this problem, I'm stuck here. I cannot scale it. I cannot scale it beyond 2,000 or 3,000 processors. That's about it. That's the physical limit. So there's really no point building a larger computer if I want to solve incompressible flow. So what do I do? So people have started talking about accelerators, right? I mean, this is the new buzzword everywhere talks about. So these are the vector machines that we are going back to. So these are the two popular competitors which are going head to head these days. You have the Intel Xeon Phi and you have the NVIDIA Tesla / Kepler CUDA kind of architecture. So these are essentially vector machines. So if you go back to their architecture, your architecture looks something like this, right? You have a really nice large cache, you have a lot of arithmetic processing units, you have some control units, but it is actually processing one instruction per cycle, generally, okay? It is processing one instruction per cycle. It operates on one data point at one point of time. So that's why it is called SISD, or single instruction, single data kind of architecture, okay? Whereas the GPU actually has many lightweight processing cores. It takes in several data and parallelly executes one instruction on it. For example, if you were to do, say, addition of two arrays on a CPU, which is of length n. Now on CPU, it would take the first element of the array, add it, put the result, take the second element, add it, put the result, so on and so forth. Go ahead, go ahead, go ahead, go ahead. Whereas in a GPU kind of architecture, it would take, depending on how many processing cores you have, it would take that size of data and do all the additions at the same time and then write it back. That's why it's called a single instruction multiple data. The analogy I like to use is this, of why CPU and GPU computing is more efficient, okay? So suppose my task is to deliver pizza, okay? I need to deliver, say, 100 pizzas in the next 1 hour, okay? I could take a big truck like this, fill it up all with pizza, and go door to door and deliver it. Or I could take n scooters, maybe 25 scooters, put 4 pizzas per scooter, and go and deliver it as well. Notwithstanding the traffic in India, this is still a far more efficient way of delivering pizza. And that's what essentially we are doing in a GPU, okay? These computational cores are very light. They don't have too many functions, okay? They don't have too many complex logic over here. but they are very, very efficient in doing repetitive calculations and working on big streams of continuous data continuously. And that's what we do in our numerical methods. We try to work with as much data as possible, as quickly as possible. Believe it or not, they're also very energy efficient. Okay, so these cards consume a lot less power. If you were to build a computing cluster, the amount of power that it consumes today is of the size of a small town. So one petaflop computer would consume roughly about 1 megawatt of power. This is including cooling loads. I mean, the cooling loads would vary a little bit from location to location, but just if you're talking about the compute power, it's going to take in about 1 megawatt of power. So if you want to do that kind of calculations, you need to become very power efficient. And these kind of cards or these kind of processors are far more power efficient. They take roughly about a third or even less power to give you the same kind of flop rating. So this is another reason why these kind of cards are not going away in the future. This is where, believe it or not, computer architecture is headed, and we don't have a choice. So in the days gone by, the applied mathematicians would devise the numerical method, and the computer scientists and the electrical engineers would go and build the computer for us, right? That's how ENIAC, etc. was built. But today, it's the reverse. They decide and they design the compute architecture, and we have to adapt our numerical methods to it. Okay? Believe it or not, the video game industry drives most of this. Okay. So you see, this is a percentage pie chart of the top 500 supercomputers which have accelerators in them. So in 2012, roughly about 23% of the computers, the fastest 500 computers, had accelerator cards. And in 2013, the number's gone up to about 34, and I'm sure I don't have the 2014 data, but this is increasing. So you have to adapt your numerical methods to this kind of architecture as well. All right? Okay. So I've created now the basis of why we need to adapt our numerical methods to the computer architecture. Now let's see what this new numerical method does and what benefit it gives us over the existing finite volume kind of methods for continuum mechanics. Okay? So if you look at so what I like to call as element-based Galerichan methods. Okay? So all these element-based Galerichan methods, they partition whatever your computational domain is into some computational elements, and then you approximate your solution using some kind of basis functions. Okay? So let's keep it general at this point of time. Okay? And if you look at it, finite elements, spectral elements, finite volume, DG, etc., all essentially come from the same family of elements, same family of methods. You can further subdivide them into continuous and discontinuous. Okay? And here, H is the number of computational elements that you have, and as you increase this, and P is the polynomial order of your basis, the polynomial order of your basis functions. And then you split it between whether your solution is continuous throughout your computational domain or discontinuous between computational elements. Okay? So obviously, if you have a large number of elements but very low polynomial order in the continuous side, you are basically doing finite elements. If you go down to a first order or a zeroth order basis function on the discontinuous side, but with large number of elements, you're basically doing finite volumes. As you increase your basis the order of your basis functions, you get to spectral elements on the continuous side, you get to discontinuous Galerichan on the discontinuous side, and this is in the limit where you basically have n Fourier modes, right? So you go into your spectral transform kind of thing, where essentially your entire computational domain is just one computational element, but you have several Fourier modes. So you go down to spectral transform. So this is how I like to see the distinction between continuous, discontinuous methods in EBG. Okay, so what are we essentially doing in DG? Okay, so we say let's start off with a canonical equation, which can look like a wave equation or something of that sort. So you have a solution Q, which is a function of space and time, and you have F, which is a function of Q, U. Okay, We begin by approximating the solution variables using some basis polynomial functions, and this could be of any order. Okay, so this can be any general order. So typically we use orthogonal basis functions. Typically in 1D we use Lagrange polynomials. If you want to go to quadrilateral and hexahedral elements in 2D and 3D, we take tensor products of Lagrange polynomials and we go ahead. If you want to go for odd-shaped elements, there are still, as long as you are able to generate orthogonal basis functions, you should be able to use this kind of techniques without any issues. Okay? Obviously, then we construct the following approximations for the different terms in the canonical equation, and we substitute it into our PDE. Now, obviously, when we substitute into our PDE, there is a residual. This is not exactly 0 because we are actually doing an approximation at this point of time. Now, what we do to resolve this issue of residual is that we integrate it over the computational element now, a small computational element. We integrate it and we drive that integral to 0. Okay? So we multiply it with a test function over here, and then we integrate it over over the computational element, and we drive it to 0. Okay? So your domain essentially is partitioned in this fashion. So this is, I'm just showing you a 1D domain over here, but this concept can be extended to 2D or 3D. Okay? And so your last integral in this expression becomes 0, and it is 0 essentially because it is orthogonal to your solution. So this is your, say, if this is your actual PDE behavior, this is your approximation, your residual will be orthogonal to it, and then you go back to your original solution. Okay? Now we start playing with our calculus. We do our calculus identity. We just use calculus identities, and we also use Gauss's theorem. Okay? And then we change that canonical equation into this form, okay, where we get this product of Fn and the basis. Okay? And when we integrate this second term, we get essentially a surface integral, which is on the boundary. Okay? Now, the moment we get this, we can start describing our DG problem. So this is where you can enforce the discontinuity between two computational elements. And I can convert this surface integral into kind of a Riemann problem now. Okay? Okay, so essentially, this represents the weak integral form, and now you will have discontinuous solutions, and you will have a jump across solutions at the computational element boundaries. Okay? Now, you have a flux which comes in from the left side, and you have a flux which comes in from the right side, which is different because you have different discontinuous solutions. But in order to enforce conservation, you have to use a numerical flux. Okay? So you have to basically solve the Riemann problem over here. Okay? And you could use any Riemann problem, any Riemann solver. Okay? So typically what people use, okay, I think, am I going back? Okay, yeah. So yeah, so you basically construct a numerical flux and sum it over all your computational boundaries of your computational element, and you use some kind of numerical flux. In this case, Ruzanov, okay? Because if you have a strongly directional flow, if you use Ruzanov or what is called a Lax-Friedrichs flux, this would work, okay? There is an entire, I mean, you could go and do an entire PhD thesis on different kinds of Riemann problems for specific kind of conservation equations. Okay? Now, if you look at it, this is in the finite volume limit, all you need to say is that your basis function psi is 1, right? Because that essentially becomes your finite volume limit. If you use any higher order basis, then it becomes dg. But if you were to substitute psi as 1, essentially saying that the solution is uniform within the computational element, you will recover the finite volume method in this case. Okay? So yeah, so this is just a math showing that we recover what finite volume method would traditionally give us. Okay, I'll skip this. So how do we go about using this? So we typically try to implement it in something like a shallow water equation if you want to model tsunamis or storm surges. I'll come back to this equation in a bit. What I want to show you first is the different kinds of basis functions we use. So I talked about Lagrange polynomials in 1D, 2D, and 3D if you're using, obviously straight lines, quads, and hexahedra. But if you want to use, say, triangles, taking tensor products no longer works, right? So you have to use some kind of other cardinal functions. So this is PKD polynomials, which are basically used for triangular basis functions. And you can see these are the basis functions for order 1 with 3 interpolation points within the element. For order 2, it would have 6 interpolation points and hence 6 basis functions. And, at 3, you would have 10 interpolation points and 10 basis functions. Okay? So if you want to apply the DG method, you would basically take the weak form of whatever conservation equation, in this case shallow water, okay, multiply it by your test function, then integrate it, and you would solve your Riemann problem. Okay? So all this is done at the local element level, not on the global domain. Okay? So your size of your problem is actually very, very small. You can then come up with the matrix form of these semi-discrete equations. Okay? So you put in your polynomial approximation, and you can define each of these elemental matrices. Okay? Now the size of these elemental matrices is very small. So suppose we are doing a 4th order approximation for a quadrilateral. So essentially we would have 25 interpolation points, right? Because you'll have 5 in one direction and 5 in the other direction. So you'll have 25 interpolation points. So the size of this matrix is just 25 by 25. Okay? And similarly, the size of this differentiation matrix will also be 25 by 25. Then you can easily invert these mass matrices because you're doing it only once now, right? You can easily invert this 25 by 25 mass matrix by any either iterative or direct method only once, and then you can reduce your entire problem, as long as you're using explicit time integration, into something like this, where you have reduced your problem into a matrix vector multiply. Okay? And I just need to multiply it with a Jacobian, and then I get this equation where I can keep on doing matrix vector multiplies to advance the solution in time. Okay? Now, let's look at the sparsity pattern for the DG method. So you will see immediately that because we are dealing with by 25 by 25 matrices for 4th order, you'll immediately start getting very, very, very dense matrices, matrix structures. And this is very, very computationally efficient. Because, yeah, you're doing more computes at this point of time, but the information that you seek is very, very local. Now, if I want to compute a higher order gradient, my information no longer resides in the next element. It is actually within my own element. Okay? And since it is within my own element, it is memory local. So I can do more and more computes once I fetch my data, and that makes it more memory efficient. This reduces the memory to compute ratio, which I talked about earlier. Okay? And you can see clearly that if I use 4th order polynomials, okay, this is scaling for an Euler code. It's quite clear here, but somehow it's not clear there. But you can see that as you're scaling, the blue line is the DG line, which is the discontinuous Galerkin method. You can see that it kind of scales near very, very well as it goes to say about, say, 16,000 processors over here. But if I increase my order of accuracy, if I go to a higher order method, I increase my polynomial basis to 8, you see that I can linearly scale in DG up to 32,000 processors over here. Eventually, at some point, it will stop, because everywhere it has to. But what? Yeah. Which deviation? The previous curve, right? Okay. You see, as it's going, it's starting to deviate from here, because at this point over here, you're having one element per processor. So you're having one element per processor, and you don't have that much compute to do. Okay. So this is 4th order in 3 dimensions. So you're talking about 125 degrees of freedom in one element, all fitting onto one processor. Okay. Now, if I increase my computational complexity, when I go to my 8th order, so it is 729 points in 3D, and hence that scales much better. Okay. And by the way, this is strong scaling. If you look at most scalability plots, people will keep talking about weak scaling, but this is actually strong scaling. Even here, at the end, it is one computational element per processor, but just that it has 729 degrees of freedom in that computational element, it has to do a lot more work. Okay, so that is the thing. I could not test it beyond this because where I was running, they wouldn't give me more than 32,000 processors. The machine had only 50,000 processors to begin with, but I could test it only to up to 32,000 processors. But you can see that the power of this method. So the point is, as you go higher order, okay, it is not only advantageous numerically because you're computing something more accurately, right? Because your order of spatial accuracy has increased, you're also becoming more and more computationally efficient. Okay, so it's kind of tries to kill two birds with one stone. Okay, and this is very, very important when we are trying to do numerical weather prediction, or we are trying to do say something like storm surge modeling, or etc. Because there is a lot of subgrid scale parameterization. We can't basically resolve every feature. For example, if you're doing weather modeling, even for mesoscale weather modeling, which is when you're down to say a resolution of 1 kilometer, cloud models are parameterized. Okay, and the inputs to cloud models and rain models, etc. If you have a higher spatial accuracy in your advection solution, it will improve the solution in your parameterized cloud model. Yes, that's a good question. That's a very, very good question. The reason why continuous Galericon does not follow that is the communication ratio of continuous Galericon is far more than of discontinuous Galericon. So if I go back here, let's see if I have a diagram for it. Actually, okay, I don't have a 2D diagram for it, but yeah. So if you were to imagine, so let's imagine a grid with just quadrilaterals, right, with 4 faces. Now, if I'm doing discontinuous Galericon, I have to communicate only with 4 computational cells. That's where I have to solve 4 Riemann problems. That's about it. 4 flux quantities I have to evaluate. But for continuous Galericon, because I'm enforcing C0 continuity of the solution, now I have to do communication with 9 neighboring elements. Because those corner elements also, I have to enforce continuity. So my communication ratio actually worsens with continuous Galericon. Okay, and when it goes to 3D, it obviously becomes a lot more. Okay, it will not do a good job as compared to DG, but it will still do a better job when you compare it to lower order methods. Because the amount of compute that you still need to do, even in CG, say 3D 8th order, you still have 729 grid points inside yourself, inside one computer. So it is still computationally heavy. But just that compared to DG, yes, it will not do as well. Get back to that. Which, in this plot or the next one? Next one. Okay, yeah. So this is actually some anomalies of the machine. Because since I'm talking about strong scaling here, in the sense that as I'm going to larger and larger processors, I'm not increasing the problem size. I'm doing the same problem size. After this point, the problem started fitting in the cache of the processor. So hence it started showing this speed up again. Okay? So until this point, the problem would not fit in the cache of the processor. It would have to still do main memory fetches. But after this point, it started fitting on the cache of the processor. So it started accelerating a little more. But eventually, it will hit a ceiling. Okay. Okay. So I talked about, now this is, okay, by the way, this is all CPU based scaling. Now when we come to our GPU based architectures, what is happening? Okay. So if you look back at my matrix form of semi-discrete equations, I have these 2 integrals which I need to compute over and over again over here, basically with my flux matrix and my differentiation matrix over here. Okay. And I can easily offload, these 2 problems are kind of independent of each other. Okay. And they are relatively embarrassingly parallel. Especially this volume integration over here, requires no communication. This flux integration still requires communication with the neighboring element, but this volume integration requires no communication whatsoever with any other computational element. So this is actually an embarrassingly parallel problem. And the higher order I go, the more heavy this becomes, right? So if I look at the GPU speed up for higher order, so when I parallelize both the volume and the flux integration, and this is comparison with on my laptop, okay? So when I go to an 8th order polynomial, I almost get 8 times speed up compared to my just pure CPU, plain vanilla CPU based version code, okay? And this is an unoptimized parallelization on a GPU. In the sense, I have not optimized for memory fetches. I have not optimized for memory occupancy either, okay? And still, I get about 8 times speed up. If you look at lower order methods, your finite volume is somewhere over here, right? Finite volume is somewhere over here. So you cannot theoretically extract that much performance out of lower order methods when you go to these GPU-based computes. So a student of mine took my code and then she optimized it for 4th order polynomials, okay? Because she optimized the memory occupancy, the fetching, etc. For a 4th order polynomial, and she got about 25 times speed up for the same code, okay? And this is phenomenal speed up considering that this is just on one ordinary GPU on a laptop. This is not one of those expensive specialized GPUs either, okay? If you were to optimize it for that, the amount of performance that you could extract is probably much, much more, okay? So similarly, she also did it on using OpenMP on an Intel Xeon Phi. The previous calculation was on a NVIDIA GPU card, and she was able to extract up to about 10 times performance in all, okay? This is some number which is speed up compared to just one thread, but this is the actual true number. This is what would happen if you actually run it on a CPU, and then if you ran the thread-based version on the Intel Xeon Phi, you would get about 10 times speed up. So we need to do further optimizations on this algorithm as well. So you can clearly see that if you want to start extracting performance out of these newer architectures, which, yeah. 10 times a single core, yes. Single core calculation, yeah. Multi-core, the same issue will come up again. But yeah, this is a 10 times a single core calculation. Yeah. So it's clearly from this analysis we have seen that if you want to extract the maximum performance, even out of a single GPU, forget trying to go towards an exascale computer, we need to invest time in newer numerical methods. And DG is one of the candidates for it. Okay, there are several methods which are out there as well. LBM, SPH, etc., particle-based methods which tend to have similar features, and DG is just one of the options for it. Okay, so now let's come up. So let's see what I can implement this to. Like, can I implement this to something which is practical, right? So I'm going to talk about inundation modeling. Okay, so this is a photograph of the 2004 Indian Ocean tsunami. Okay, this is a wave which is coming and hitting Andaman Islands. Okay, now tsunamis are still rare events. We have had some 3 major tsunamis in the last 10 years, but they're still decadal timescale events, right? What happens more often is storm surges. So this is the devastation left by Hurricane Ike back in 2006, 2007, I think, on the coast of Texas. And this happens multiple times in a year in multiple locations. And we really need to understand the physics of this problem and try to implement and see if we can come up with good solutions. Okay? So we typically use shallow water equations to solve this kind of problems. These are nothing but 2-dimensional depth integrated Navier-Stokes equations. Okay? And the source for, so if you look at a tsunami problem, it is an initial value problem. You have some initial seafloor upliftment. You have a gravity wave which goes and creates whatever destruction it is. So you just set up your initial condition and then it goes and does its thing. Whereas a storm surge problem is actually a boundary value problem, okay? Because you have a continuous forcing which comes in from the wind stress, which is kind of acts like a source term over here, okay? So just some terms, the phi, which is the depth, integrated depth, is known as geopotential height, which is g times the height, the depth of the ocean. Oceanographers like to call the depth of the ocean as bathymetry. That's another term which people talk about in this kind of calculations. Okay, so storm surge is usually driven by wind stresses which come in to this source term over here. Okay. Now, when we come to the inundation model, essentially it's a moving boundary problem. So you have a shoreline, and this is your ocean out here, which is your computational mesh, and this is your dry land. Now, what closes this moving boundary? What are the typical forces that close this moving boundary? Now, that's a grand challenge question. If you were to think of just purely multi-phase flows or droplet dynamics or things of that sort, you have very good conservative forces which will close this interface, that's surface tension. But in modeling shorelines, we don't have a conservative force which will actually close this. So it's really hard to model this moving boundary. Okay? So the way most people try to model it is they take the entire region as part of their computational domain, and then they play tricks with their governing equations or their numerical method to distinguish between dry and wetland. And then the interface is obviously somewhere in between in this computational domain. Okay? So you typically have a moving front which is defined by the interface velocity. Moving grid methods are typically cumbersome, mainly because of the reason which I mentioned. Fixed grid methods are easier to implement, but what we really need to maintain is something called as depth positivity. You don't want at any location your mean sea level water height to become negative, because that doesn't make sense, right? So effectively, what you do is you modify your algorithm. And in my case, what I'm trying to do is I'm modifying my Riemann solver. Okay? I'm using my Riemann solver as a control to see to it that I maintain depth positivity. Okay? So you have your initial problem. So what I say is that there is a minimum threshold below which, if the water surface height falls, I tag those computational cells as dry, and then I modify my computational solver in such a fashion to handle those dry cells. Okay? So I want a solution like this. If the sea level keeps falling, I would have a thin film of water which would be considered as dry. And now this can be of the region of, say, 1 centimeter or something of that sort. So if it's something like 1 centimeter, fine, it is dry land. Okay? What I don't want is to end up with a solution like this. This is a bogus solution. I cannot work with that. So what we do is we modify the conservation of mass equation, right? So we limit the geopotential to a minimum threshold. Now, once I limit my geopotential to a threshold and I integrate my conservation of mass in time, I have an error in my flux term. Now, I appropriately modify my flux term to ensure the fact that I maintain depth positivity and also conserve mass. Okay? Conservation of mass is very, very important in this case. So essentially, if I go back to my matrix form of equations, there are two integrals. There is the surface integral, which takes place, which is basically the Riemann solver on the computational element, and you have the contour integral, which distributes the solution within the computational domain, the element, sorry. Okay? So what I do is, I say that if there is a dry node, i.e., I am at the threshold, if I have contributions coming into this dry node from a node which is within this computational element, I allow the solution to come in. But if the dry node has to contribute something out, if there's net flux going out of that, I make it 0. Okay? Similarly, if a computational element has a dry node in it, you have numerical fluxes. I control the Riemann solver. You have the numerical fluxes coming in, that is allowed. But if the numerical flux is such that you have mass leaving the computational cell, then I don't allow it. I just cancel it out. So if I just take care of this accounting, then I have conserved the mass and I have also resolved the issue of depth positivity. Okay? So right now, my algorithm, I'm stuck using at the interface to using linear elements. I'm not able to go higher order, but I'm working on trying to make this algorithm into a higher order. The point is, if I'm for complex coastlines, I use triangular elements. So in linear elements, I have only 3 points. So the moment I tag one point as dry at the threshold, I say that that element is dry and I don't allow fluxes to go out of it. If I use a higher order element, then making that decision becomes harder, because now I have 6 computational nodes on which I have to make the decision. So that is the reason I'm trying to figure out what is the best mechanism to make this decision. Okay, so yeah, so to put it in a nutshell, you have wet, which is allowed to get into dry, but the other way is not allowed. Okay, so armed with this algorithm, I tried to do some tests with the 2004 Indian Ocean tsunami. Okay, this is a plot of the bathymetry of the Indian Ocean region. This is a computation, very fine computational grid, not as fine actually. You could get much finer than this. And this is the actual simulation of the 2004 Indian Ocean tsunami. You can see the wave propagate. Actually, it turns and even comes up the west coast of India. The wave was actually measured as far as Goa and even in Gujarat. So the wave kind of propagated to big distances. Okay, fine and nice calculation. Here is the nice eye candy media version. This is the depth of the ocean. Coast of India, you have the waves going. So if you want to just, show it off, you would like to show it off in something like this. But the meaningful science comes here. And again, for some reason, the plot is blurry here. But anyway, I'll try to explain. So this is at, there were tide gauges in the ocean, which actually measured this event. So what it was basically measuring was the arrival time and the arrival height of this wave. Okay? And you can see that this is at Vizag. The red line is actually the measured tide gauge information of the wave height, which has been detided. Okay? And green is the prediction of the model. And you can see that there's relatively good agreement of the arrival time and arrival height over here. In Madras, in Chennai, you can see the arrival time is kind of fairly well predicted, but the arrival height was off, in the sense the model kind of over predicted the arrival height. Okay? And I'll get back to why we are having these anomalies as well. I mean, there are several uncertainties in this calculation. Similarly, you have arrival time and arrival height at Goa, and this is in the Maldives. Now, one of the big important factors in this calculation is the bottom friction of the ocean, and which is not uniform. Okay? The accuracy of the bathymetry data. Because a tsunami simulation, a tsunami wave actually behaves at like a gravity wave. And the propagation speed of this wave is square root of GH, where H is the depth. Okay? Now, if you have inaccuracies in your bathymetry data, or you don't resolve your bathymetry enough, like if you run a coarse simulation, you're going to be off in your, the wave speed, and hence your arrival time will get affected. Okay? And your secondary wave, etc., will get affected by the bottom friction. Now, I just assumed a uniform bottom friction for the entire thing, but in reality, that's not true, right? I mean, you have to have, you need to parameterize it and everything. Okay? So this is kind of like a first cut calculation, if you want to believe it. Okay? So similarly, for the storm surge simulation part, we're still in the early stages. So here I just put an idealized storm, which is I took some analytical wind model and put wind shear stress and set it off at a 45-degree angle to the Gulf of Mexico coast. So this is like the shear stress on the ocean which is going. So, and then when you see as the eye of the storm moves, you can see the waves arriving actually much earlier than the actual eye of the storm. Okay? The surge typically arrives much earlier than the arrival of the eye of the storm, and it also affects parts of the coast which are much further away from the eye of the storm, and this is kind of routinely observed in meteorological calculations and observations. Okay. But if you look at tsunami calculations, really what we want to solve is the inverse problem, right? Because real-time compute of this event is actually a challenge. Even say, suppose we are able to solve it, we have the computing power to solve it, okay? There is significant uncertainty in the initial condition. Like when an earthquake takes place, typically when the earthquake took place in Indonesia, I think there was a lead time of about 8 hours before the wave actually hit the Indian coast, much sooner in Indonesia, obviously. But the uncertainty in the initial seismic condition itself, even today there is uncertainty in the initial seismic condition. So it's very, very hard to do a real-time compute and to do a real-time prediction. So what government agencies or emergency agencies would really like to do is to keep several scenarios ready and do a superposition of them. Okay, so you want to compute really a wide spectrum of possibilities and then come up with identification of vulnerable areas and what should be the evacuation routes and what should be the strategies. Okay, to do. So you typically you want to generate what is known as inundation maps. Okay, so this is an inundation map of Bali where they have identified under various scenarios which is the most probable locations where flooding, etc. could occur. And looking at data like this, city planners could then go ahead and plan for any emergency and mark out what are the evacuation routes. It's also kind of useful for insurance companies, because if you want to in the red zone, you probably want to pay a higher premium on your house insurance. Okay, so the current state of the art is you do calculations with a resolution of about 100 meters, 50 to 100 meters, but you actually want to go down and do calculations at 5 meters. You also want to resolve urban structures. So if you look at what happened in Fukushima, there was a lot of live video coming out of that event. You see how the wave came and affected urban structures, and actually there was a lot of the wave characteristic changed because of urban structures as well. So it's not just about having the correct bathymetry data. Once things get on shore, we also need good information of how the urban structures is and how to resolve this. Okay, so my closing arguments would be that to solve complex problems like the case that I showed for storm surge and tsunamis is that we need more than ever computational power, and current numerical methods have scalability issues. Finite volume methods, etc., don't scale well as much. And so the biggest argument is that numerical methods have to adapt to newer computational hardware rather than vice versa, because we can't go to Intel and say, hey, design me a chip which will do CFD better. It's rather than Intel will put out something and say, we have to figure it out. Okay, thank you. That was the end.